there could be an entire universe that is running backwards that we can't even see.
And the slowest they can move is the speed of light.
Is the speed of light.
It would take an infinite amount of energy to slow it down to the speed of light.
Ooh.
This is StarTalk Special Edition. I'm your host, Neil deGrasse Tyson. I got with me Chuck Nice. Chuck.
Hey, Neil.
All right. And of course, Gary O'Reilly.
Hi, Neil.
And Charles, welcome back to StarTalk.
Always a pleasure. Thank you so much.
Totally in the family.
I feel like I'm in the family. I'm honored. Thank you so much.
Excellent. So let's get started. We solicited questions for this, and we got like 140 questions.
Dang.
And we will. Yeah, I know, right? So that would be
that's the point we stopped counting.
that's a question every 12 seconds. So
Wow.
Charles, get your soundbite mode ready, but we don't want to lose depth and nuance. Charles and I have extraordinary overlap in our general scientific expertise, but Charles extends beyond that in ways that render unique participation in cosmic queries.
Wow.
So,
and you extend the other way too. Neil.
No, what do you mean the other way? There's no other way. There's no way.
There are many ways to extend in the universe.
Gary, what you got?
Let's start with Fabiola Horvath from Hungary. She does name the place which she's from, but I will not be attempting to mangle the language.
Okay, give it to Chuck so he can mangle it.
Yeah, well.
All right, there's an S, there's a Z, there's an E, there's a K, there's an E, there's an S, an F, E, H, E, R, V, A, R, and there's lots of little ticks above.
Yeah, the ticks make all the difference in Hungarian. What a marvelous language it is, by the way. It's the Magyar sort of origin is completely different from like Latin-based languages and so forth.
We do
marvelous.
that.
By the way, if you want to say bless you after somebody sneezes in Hungarian, this is probably the one word I can pronounce in Hungarian. It's egészségre.
That's too much.
No, 5 syllables. It's like your whole health. You know?
Yeah, we just say bless you. And, but egészségre, that sounds like the actual sneeze itself.
Instead
that sounds like you sneezed and then I sneezed back. That's what that sounds like.
Yes. Well, you have to be careful because if you mispronounce it, instead of saying to your whole health, you wind up insulting the person's anatomical parts. When you said egészségre that way, you did great, but you got to be careful because if you do it wrong, someone will slap you.
If you say it wrong, what exactly are you saying?
You are making comments about their posterior.
Well, that could be a good thing sometimes. You know what I mean? I mean, sometimes, making a comment about somebody's posterior is very positive.
Next week on Scientific Babel, we'll be traveling to other countries to learn how to insult the locals. Fabiola, we are going to get to your question because I think it's a great question. Is it true that every single electron in the universe is the same one? Can you explain this theory, please? Even if not true. Many thanks.
Charles, this was once explained to me by Richard Gott back when I was at Princeton, and it blew my freaking mind.
We have to give you this because the person who came up with this idea is another Princeton great in the field of science, John Wheeler.
Wheeler?
Yeah, the story was that John Wheeler told this to Dick Feynman at Caltech, another giant.
Other people call him Richard Feynman, by the way.
Charles
Liu.
Sorry.
Dick,
sorry.
Okay.
Well,
it's like Isaac Newton. I call him Ike. So
right.
Richard Feynman tells the story in his work. He wrote a lot, of course, about physics, about this conversation that he had with John Wheeler about the one electron universe. But I need you to tell it because Rich Gott. Rich Gott, one of the greatest, again, tremendously interesting physicists, astrophysicists, even specifically.
Okay, so here I'll
go for it.
I'll attempt it, and then you fill in the gaps.
Okay.
So what we know for sure is that every electron we've ever measured is exactly the same.
The same. Okay.
There is no property about one electron that is not precisely represented by other electrons. So we have to ask, does that require an explanation? We might ask. Or do we just allow there to be all these electrons in the universe made in whatever way they got made and they're all exactly identical? So the question was posed, maybe they look identical because they are the same single electron. How might that work?
Yes.
Please. Yes.
Yeah.
How?
Okay.
How?
Now, right. Now we're getting to the good stuff. Yeah. Because
Okay.
right now you sound like every person describing a black man leaving the scene of something.
Oh.
They're all the same.
Yeah. I'm just saying, I thought it was him.
So antimatter, which was predicted by Enrico Fermi, if memory serves, within a couple of years, it was discovered. We discovered the antimatter particle to the electron, which we call the positron. Okay. And that's weird because all the properties are like the inverse of the normal particle. Is there any way to understand this? And it turns out one can interpret antimatter in certain situations as ordinary matter moving backwards through time.
Whoa. Wow.
Okay, it solves some equations regarding antimatter. So if you allow that, then you can ask the question, if one electron goes forward in time and then reverses going backwards in time, and it just keeps doing that, then wherever you are in time, you will see this record of electrons moving forward and backward in time in the instant that you make the observation. No, you have to pick me up from,
You did it.
Bail me out here. Where I'm a little fuzzy are some of the electrons we're looking at actually ones going backwards in time that we happen to catch in the moment we measure them, thinking they are ordinary electrons going forward in time?
Probably not. At this point, the reason we say probably not is, well, aside from the fact that we haven't been able to prove that experimentally.
Wait, don't disprove it yet.
Okay.
Just give me the full hammer of the explanation that accounted for every electron being identical, and then we can debunk it afterwards.
Right. Well, it has to do with relativity, right? Because you're moving forward and backward in time, being able to think of world lines in special relativity of particles. Now, if you imagine that things could just keep going past, present, back and forth, but you do it almost infinite number of times, then every time you measure an electron, it's the same one, but just at a different moment in time. It's a different part of its world line.
Oh.
So it's always coming backward and forward in time, right?
Okay, but so there's the electron that's in my experiment, but now I look out the window and I see a tree. That tree has electrons in it. So the electron that's in the tree and the electron that's in my experiment, it's the same electron just on a different world line that's crossing my present in a different location.
Yes. Beautifully said.
Ooh.
That sounds crazy.
Yes.
I'm just going to be honest. That sounds insane. Okay.
Well, a lot of things that sound insane when they're originally proposed turn out to be indeed insane.
Not that insane.
A lot of the stuff, though, you have grains of truth from which reality can then be further explained by it.
You had me up until the electrons going back and forth in time on a different world line in different places at the same time.
Yeah.
That
Because Chuck, the whole point of a world line is time
it's
is just one
yours.
coordinate.
It's yours.
Wait, hold on.
It's okay. Go
Wait,
ahead.
hold on. Time is just one coordinate.
Right.
So two world lines can exist in the same time, but not in the same place. That's why you can cross the street
Right. Exactly.
and not get hit by a truck. In that case, you're in the same place, but at different times. Okay? Only
Okay.
when world lines actually intersect are you in the same place at the same time. And so all these other world lines is a different world line in an infinite number of passages through our universe. So our universe would be the construct of not an infinite, you can probably number them, but a hugely high number of passages of a single electron.
Okay. So do any of those world lines ever intersect at any time?
Well, we can smash two electrons together.
Okay, so then how's that the same electron? Boom! Nice for the win! For the win! That's what I was saying. It's insane.
Charles, get me out of that one.
No, it's because you're traveling backwards and forwards in time. If Wheeler was correct in his hypothesis, because you're going forward and backward, you're literally crashing one of them that's going forward with one that's going backward, creating an annihilation, antimatter basically, positron kaboom kind of thing. So the electrons, if one electron hits the other, they're not actually hitting like we think of like two rocks hitting each other, but their wave functions are interacting in a specific way. So you see, it was an imperfect hypothesis or model to begin with, it's true, but you squirm your way out of it using quantum physics. And the idea that time is this dimension that you can go backwards and forwards. It's the melding of special relativity and quantum physics, electrodynamics.
Is it the same electron with different reference points? Is that the deal?
You could think of it that way.
Okay.
It's not a wrong way to think about it. Yeah.
Okay. All right. Okay.
But the point is, Charles, the idea taken to its limits could not be verified. The idea that antimatter is regular matter moving backwards through time does have merit.
Yes.
Correct?
And it had so much merit that Richard Feynman wound up putting it in his way of thinking about particles and the whole quantum electrodynamics.
And his way of thinking is the way of thinking, right?
At the moment, that's right.
Okay.
It's not just, he's got his way and somebody's got their way.
We don't call them Feynman diagrams for nothing.
So if I want to know more about this, because my head hurts right now, and once that's passed, I would want to know more about it. Where do I go?
Dr. Richard Gott.
Mm-hmm. Will he tell me everything I need to know?
Not to say too much about this gentleman, but would you agree, Neil, that Richard Gott might be the most interesting person to listen to for a long time? If you just had a lot of time, just
I've already thought that through. So I say to myself, if I'm in some Spanish Inquisition prison, shackled to the wall, and there's one person next to me for years, just because I'm a prisoner there, who would I choose? I would choose Rich Gott.
Yeah,
Okay.
it's a fun thing to think about.
And they say, who do you want in a foxhole with you? It would not be Rich Gott because I'd be too distracted listening to his story.
Yeah.
We would just get shot by any. No, I would say, hey, come listen to this.
Yeah.
Before you shoot me,
Yeah.
come listen to this story.
If I had just some time to sit around and just listen to someone talk about cool things and explain weird ideas in a really understandable and fun way, Richard Gott would be definitely one of them.
But that's one of the reasons why one of my books titled Welcome to the Universe.
Ah, that's right.
It's basically a textbook intended for you to read, not for you to use in a classroom. And Michael Strauss.
Yes,
co-taught
another wonderful
Intro
scientist.
Astrophysics.
Yeah.
And we each have a third of the content of that book. And you get to see his contribution to cosmology and why it's weird, wacky, and fun in that. So I knew it when I was at Princeton and we're co-authoring.
Yeah, no,
So,
they're great.
Well, I have spent an inordinate amount of time with Joel Gott, and I find that the more time that I spend with Joel Gott, the more interesting
That is a
everything
wine
becomes.
for those who don't know.
Yeah, for those of you who don't know, Joel Gott is a wine.
It's a California wine.
Yes, it is.
Plus, Richard Gott has a book called Time Travel in Einstein's Universe, which are all
Wow,
the ways
that's
that you
right.
can use relativity to engage not only forward, but also backwards time travel. So
I have a vague memory of him holding up a glass model one time.
That was different. That was a universe that creates itself, which removes the need to have an origin event.
Wow.
So it looks like a flugelhorn or something. But let's get to the next question.
All right.
That was not a fast answer. Now we're down to 139 questions. All right.
All right, so let's move on. This is from Jay Swami, who says, hello, Dr. Tyson, Dr. Liu, Lord Nice, and Gary. Jay Swami from San Jose, California here. Hey, Dr. Tyson, you always say we are prisoners of the present in perpetual transition from an inaccessible past to an unknowable future. The quote often resonates with me. Is time itself multidimensional? Could there be a higher dimension of a time beyond our single arrow of time that we experience? This concept left me puzzled, but curious about the possibility that time might not be one-dimensional. Could there be more than one dimension of time? We're just accessing the one dimension that is available to us. Is this a possibility according to current scientific understanding?
So I have a cop-out answer.
Uh-oh.
I don't see anything preventing time existing in more than the single dimension that we experience. I would just have no understanding of what that would mean.
Right.
Because when we think of coordinates of like X, Y, and Z, you can move in 1, 2, or all 3 coordinates at once, right? That's moving in the grid of the, in the Cartesian grid. And if I had a time grid, it means I can go in time this way, but not that way. And what would that take me out of my, I don't know. I don't know what that would mean.
How does this weave back into the single electron going backwards and forwards?
You don't need more than one dimension of time to have the single electron to be true.
No, I'm just wondering, does it all kind of find itself weaving itself together?
Well, time is a funny dimension, right? If you look at the way that general theory of relativity shows time, it is a dimension, just like length, width, and height. But the way the relativity is structured, the element of time in the metric is negative, as opposed to the others, which are positive.
Okay, what you're saying is time is not treated. Yes, it is a dimension, but it's not treated the same way.
Right.
There's a negative sign where X, Y, and Z have a positive sign.
That's right.
So that already admits that there's something different going on there.
That's right. And so I would say that, Jay, your question might be most easily thought of in the concept of compactified dimensions. A lot of times right now we are thinking in string theory or in other ways of thinking about space and time that maybe length, width, and height themselves have dimensions tied in with them, each of them much smaller than the Planck length or the detectable length, but they're kind of nestled within one another, right? I think Neil,
is there a way to unfold them? Those
possibly,
dimensions, can they be unfolded?
Well, right now we can't, right? But the example, I've heard Neil use this before, right? If you go right up against the Alaska pipeline, then it looks like it has length, width, and height. But then if you drive like 10 miles away, then it just looks like a
straight
single
line.
The other dimensions are there, but we couldn't see them unless we zoomed in really close. So imagine if you were looking at the time dimension or trying to figure out something traveling in time, but you were able to focus to such a fine degree of time that you could actually see other time kind of curled in there. Then you would have this extra rich dimension. It might not affect causality in our universe at our size scales and time scales, but it would still be another time dimension.
But what would it mean?
I don't know. Look, that phrase of yours about being prisoners of the present is very true, but I prefer to think of it a little bit differently. Same concept, but with a different attitude going toward it, as expressed by Master Oogway in the classic movie Kung Fu Panda, right? Which I will paraphrase saying, yesterday is history, tomorrow is a mystery, but today is a gift, and that's why it's called the present.
Oh, okay. That's. I got to tell you, that's very deep for a Pixar movie. Yeah.
It wasn't Pixar, actually.
Oh, I don't know who did it.
It was an animated movie. Yeah. But it's the same idea, right, Neil? We experience the present at the moment simply because of the way time is structured.
So wait, is there a dimension, higher dimension, where time is not experienced as a present or a past or a future? Maybe it's just experienced. So it just is. And at that point, you're able to see anywhere on that timeline, so you're no longer a prisoner.
Yeah, that's the theme in Kurt Vonnegut's novel Slaughterhouse-Five, where the protagonist is in his backyard and he's lifted up by aliens, which I always want to have happen to me when I go to anybody's backyard at night and I look up.
Right.
I want to be abducted by aliens.
Yeah, but no,
I know where that. You chuck.
Yeah, you know where that leads. Yeah, we don't want to. You know the next step. That's important.
Okay, minus the anal probes.
Okay. All right. Okay. All right. Okay.
We pre-agree. No anal probes.
Okay, that's another dimension to explore.
But anyhow, so he gets put in this sort of hyper prison, but it's outfitted with everything he likes and cares about, and he can see his entire timeline from birth to death.
Ooh.
And he can access any point in that timeline.
Ooh.
And so it explores how constricted our vocabulary is, because you can say, well, when were you born? And his answer becomes, I'm always born.
I'm born.
Yeah. And when
I am born.
I'm always dying.
Right.
When were you? I was always there.
I'm always right.
And so he can re-enter the timeline and re-experience it with very limited memory of having been there before. That was just a plot point that they needed. But the point is, that was my first encounter with time being a dimension that you can enter at any point, in the same way you walk into a room and you can access any point in the X, Y, Z, the height, the width, or the depth of the room at will. So if you can do that with time, I mean, that's quite you need a higher dimension to exit that and come back in.
Can come back in.
So you imagine coming up from, here's your time dimension line, and you're watching it from way up here, kind of like you're miles away from the Alaska pipeline time. And then you can sort of see it. Now, the pipeline is there, and it's always existing because that's the time dimension. But imagine if the oil in the pipeline was just starting to flow, and it hadn't filled up a further part of the pipeline. That's the future, where the dimension has not yet been completely filled. And that might explain causality. Whereas in the Slaughterhouse-Five idea, everything's already been filled, and you just don't know. And once you get closer, you can see it, and you can reinsert yourself.
So what you're saying is a variant on this entire timeline in full view is you have the full view of everything that's already happened.
Yes.
And so you are then moving forward in your timeline, creating the future as you go along.
Correct.
So that the future remains not only a mystery, it's indeterminate.
Yes. That's right.
Interesting.
That'd be a variant on it.
All right, I think we've just answered the next question.
Oh, okay.
However, let me read it and see if this is actually factual. Good day by Jared. Jared's in Down Under. And he says, then he caveats that way, is there a down? Fair enough.
My question is the center of the earth, but go on.
Right.
So my question is about the illusion of time. I often wonder if time is not a direction, but rather a ledger or book that records the state of everything. If nothing changed, time would not pass. If you could rearrange objects or particles, you could return to any state or moment in time, be it past or future. Is it possible that time doesn't speed up or slow down, being only a book, but rather objects have a variable rate of change based on gravity and speed? Thank you, Star-Lords, which I think applies to. So you three. Certainly, Star-Lords, that's definitely an up in the ranking. Yeah. So have you answered that question already?
Well, no. So Charles, I like that question because it's first admitting.
Yeah.
Maybe it's not that there is no time if nothing changes. There's no measurement of time.
Yeah. Yeah.
Right. So if the whole universe was static and I bring in a clock that does have some periodicity, I can measure the flow of time, even though it won't matter to anything else in the universe, only to the clock itself.
To the clock. That's it.
Yeah.
Right.
If you have the structure there, regardless of what it does, right? It's true. Not from the physics point of view, but from like the human experience point of view. There are plenty of people who advise that time is a resource, right? We as humans have only a certain number of hours in the day. How do we use that time most effectively?
Time is money.
Multitasking. Yeah, those kinds of things, right? So there's different ways to think about time in that sense. And then the idea of time as an illusion is if everything that humans invent or think about is an illusion compared with the actual physics of space and time, then what you can say is that the faster you move through space, the slower you might move through time. Your experience of time, the time is just there, and your experience of it varies depending on your velocity through space.
So in that case, time becomes like a lake and we're all just swimming in it.
Right.
Yeah.
And how much do you wish to drink of it at a time? Do you sip from a straw or do you try to gulp from a fire hose? Right.
Oh, look at you getting
Man.
all damn.
Man, getting all poetic and stuff.
I tried to drink from a fire hose once. It was fun.
It's hard.
But, that's hard.
Yeah.
Knock your head off.
I'm just going to tell you, as a black man, something I've never had a problem with.
No, it's something you're not going to attempt.
Exactly.
It's got bad vibes.
That's what I mean when I said not a problem with. Like, I've never been curious.
Well,
yeah, exactly.
To be fair, it wasn't aimed at me. It was sideways.
Oh, okay, cool. Yeah.
Still. I'm not sticking my head in front of a fire hose. That's not got bad vibes. So let me make two factual statements, I think. In a universe where nothing is periodic, there can be no measurement of time. All you can reckon is a sequence of events from your own perspective. So you can have a before and an after, but you can have no measurement of what occurs between them.
You can figure out entropy. If you knew what the total entropy of the universe was.
You have an entropy clock.
Yeah.
Ooh.
Yeah.
Ooh.
As a function of how disordered the universe is, if you believe the historical era of time goes from low entropy to high entropy.
High entropy.
Yeah, that's not a belief, it just is, right?
Yeah, we have a clock like that. It's the countdown to the end of the world through climate change. So.
How's that coming along, Chuck?
Quickly.
Not looking good.
So, all right, look, we got more here. Look, Gary, what do you have?
All right, let's go with Isaac Kinsey. Hello, Dr. Tyson, Dr. Liu, and Lord Nice. My name is Isaac from Indianapolis. My question is about quantum wave fields. All right.
Ooh.
Is it possible to detect quantum particles or quantum wave fields that don't interact with gravity or the electromagnetic wave field?
Wow.
Up to you. Here we go.
And Charles, you've just written a book about the quantum. What a nicely timed question for that. Well, glad you wrote your book just in time for this question.
How much did you pay Isaac to slip this question in at this very opportune moment?
Well, I was able to observe the timeline from a distance and saw that this was happening, and so I've inserted myself into the time.
Just to remind our audience, you're author of a couple of books in this series, like explainer books, very accessible, very dip-inable, if I remember correctly. The title of this one is what?
This one is called the Handy Quantum Physics Answer Book.
Ooh, Handy Quantum Physics. Said no one ever before.
Yeah. I liked your other one too, the Handy Heart Surgeon book.
No. The first one in the series was the Handy Astronomy Answer Book that I wrote, and then the second one was the Handy Physics Answer Book. And this one is focusing in on quantum physics, because the physics book we could only glance at the surface of any specific area. But quantum physics itself is so much fun. Now, everyone should know that I do not do research on quantum physics itself, although I use it in all of my science all the time. And I wanted to, for myself and for anybody else, be able to explain basic ideas of quantum physics, which feels so mysterious and unknown, but actually is all around us on a daily basis. And so it's not an attempt to sort of decipher the deepest mysteries of quantum physics, but the idea of just talking about how cool it is and what we know already and what we're still thinking about in the future.
Yeah, in our field, we are formally trained in quantum physics because it shows up, and it's like a necessary thing you got to deal with. But we don't spend our living days questioning the philosophical foundations of it. Does it work? Give it to me. I'm going to use it.
Right. But it's fun, right? As we've had these questions in this particular episode, that's very much deeply involved in our imaginations and our questions. And so talking about giving the framework of the normalcy of quantum physics gives us the opportunity to think more deeply about the abnormalcies, shall we say, of quantum physics. So yeah, it's kind of fun. It's a neat book. I enjoyed it, writing it.
Okay, so how about that question? Can you measure the wave field without it interacting with electromagnetic energy
or gravity?
Yes, and we already have. There is a force field called the strong nuclear force, right, which is neither gravity nor electromagnetism. The particles in there are gluons, right? They are massless, and their kind of charge is known as color charge. And they are the particles called bosons that do not interact directly with the electromagnetic field or the gravity field. It has its own field. It's the strong nuclear field, or quantum chromodynamics is the sort of semi-formal way of talking about its theory. So the answer is yes, great question, and there's a lot of cool work going on about gluons.
And why a color field with the word chromo in there as well?
Right.
So why color field?
It's physicists are racist, and they.
Well, the colors are red, green, and blue.
The yellow
so...
particle, the red particle, and the black particle.
Now, we wanted to express as physicists that there was a thing that was like charge, but wanted to make sure that no one confused it with electric charge being positive or negative.
Gotcha.
This kind of charge, color charge, right, that has three, right? Red, green, and blue, by coincidence, RGB.
Of course.
Yeah. And so there are 8 types of gluons. All right. You might think that there are 9 because 3 times 3 is 9, but it turns out that one of them is degenerate with another. So, yes, insert your own joke here.
Exactly.
Physical degeneracy and all that, right?
Hey, little gluon.
So as I called it quantum chromodynamics to distinguish it from quantum electrodynamics. And it's a neat field. It's only contained within this little tiny environment within subatomic particles. But it's so important because, for example, we know that if you add up the mass of the quarks that make up a proton, you get much less than 100% of the mass of a proton. So all the rest of that mass is in the form of the energy that the gluons holding this thing together has. And so
gluons are massless.
Right.
So
Right, yeah,
the mass you're measuring is contributed by their energy content.
the E equals mc squared conversion.
Right.
Okay.
And it may well be, although this has not yet been confirmed yet in an experimental way, that the gluons and the quarks may be moving back and forth in an electron, changing their existence and their states. It's almost like there are valence quarks and then there are dynamical quarks, I don't remember the exact name, that kind of slide back and forth and become gluons or non-gluons and quarks and antiquarks. A proton, as stable as it is, as much as it is the bedrock of all matter as we understand it, is still very possibly a dynamic and fascinating object. And this quantum chromodynamics and this kind of interaction with neither the gravitational nor the electromagnetic fields is what produces this fascinating physics.
All right, let me back up here. So,
Damn.
if you
That's
wow, you just went outside of his list,
Yeah.
to find something that could interact with a quantum wave field.
Mm-hmm.
Okay, but if you subtract away our 4 known forces, okay, the strong, the weak, the electromagnetic, and gravity, does the wave function go unperturbed at all? Can dark matter, dark energy, collapse the wave function? Or is it immune from that? Do we know?
I don't think we know yet. Dark matter, as you know, Neil, is one of the most unusual ideas that has been experimentally confirmed, but has no theoretical explanation.
That's why I'm asking. Is there something that the wave function can elude? I guess that's really what I think that question was after.
Yeah. At the moment, we don't know. It may be a dark matter particle, but remember, dark matter interacts with the gravitational field, right?
Yes,
That's why we know of its existence.
Right. So, okay. But say that again, because I'm really trying to grasp that.
Right. Dark matter has been observed.
Like, so we observed
know it exists.
Well, okay, right.
All right, we know
because
it's
we've seen the effects, is what
Yes.
you're saying. We've seen the effects.
That's right.
Chuck, you are more correct in that moment than Charles implied. Okay. So it's not that we have measured dark matter. We have measured a source of gravity whose origin we do not know.
Okay.
And we call that source of gravity dark matter. But to say we've measured dark matter implies that there's a thing called matter that we have measured. We've measured no such thing.
Right.
We've only measured the gravity, and whatever dark matter is, it has gravity. And that's why we can say it interacts with us gravitationally.
Wow.
But it doesn't interact with us electromagnetically. Light just passes straight through.
Right.
We have molecules in our body that are held together by the electromagnetic force. There's no such counterpart in whatever is going on with dark matter.
And what we've done is tried over and over again to posit the existence of particles that could behave the way that we've observed them, but no experiment has yet been able to detect any such particle.
Things we don't know. Put it on the list.
That's God, what an exciting frontier, though, when you think about it. That's
neat.
Really cool.
All right, let's throw another question in there. Let's come away a little bit from quantum for a moment. David Klingbeil. Hello, Dr. Liu, Dr. Tyson, Lord Nice. Dave's in Palmer Heights, Ohio, and all I can think about now is Palmer ham. Sorry, thinking with my belly again. Orange looks like a mixture of red and yellow because its wavelengths lie between them on the spectrum. Green looks like a mix of yellow and blue because it lies between them. Why does violet look like a mix of red and blue when it does not lie between?
Oh, that's a great question.
Look at that.
It has to do with quantum biology.
Ah.
Our eyes. We have those rods and cones in our eyes, right?
Charles, I want you to finish, but I want to preface it by saying we need to separate here the physics of what's going on from the biology of what's going on.
Yes.
The physics of what's going on is there exists pure orange light that is not a combination of anything, right? There exists pure green that is not a combination of anything. It's a wavelength of light that can be specified unambiguously. That's why in our field, we don't really... We make pretty pictures, colorful pictures, but we don't talk about colors in the way everyone else does. We talk about the bands of light and where they are on the spectrum. Okay, so now let's bring in some physiology.
No, that's fair. The way that Neil is describing is 100% correct. And violet light actually has a wavelength range where it's actually unambiguously violet. But our eyes don't actually detect that very well. Our eyes process color when photons hit and activate our cone cells, right? Whether they're the red or the green or the blue sensory cone cells. And so what we perceive as purple or violet, or more accurately, magenta, right, comes from the interaction of the red and the blue cone cells processing in our brain to create a thing, which is not the same as the violet wavelength color that comes off of, say, a physical process or a hot object or something like that.
Okay, so when those photons are hitting our cone cells, are we actually seeing the wavelength or our eyes creating that color? Because there would be two totally different things.
That's a good question.
The best way to think about it is that our brains create that color based on something that is not exactly straight physical. Like if you look through a filter that specifically channels violet light on the spectrum, you can actually see stuff coming through it. But that violet production, that once it gets into our eyes, those violet photons come in and they do things and they produce like the same kind of violet that we would process with our brains when we see a purple t-shirt, but it's not been produced by the same physical process.
Wow.
Yeah, it's cool.
That. You make coloring exciting. You make coloring exciting, Chuck Liu.
Color is exciting. Vision and so forth, right, is very often most easily explained by thinking quantum mechanically. You have photons coming in and hitting us, as opposed to all these weird electromagnetic waves that kind of excite this and that. But a lot of biology is right at that intersection. We thought we knew that, this humans smell by this, or humans see by this. But there's physics right between that layer of the organ, the eye.
All right, one last quick question. So when we make sensors that actually look out into the universe, are those sensors specifically tuned to the wavelength?
Yes.
Okay.
Excellent question. Yes, it is.
But we can take three sensors to three different wavelength bands, and after we obtain those data, we can slap on a red, green, and blue filter on them and create a color picture that you would see if you were out there in space and our cones were sensitive in those three bands.
Right.
That's how we can make color pictures outside of the visible part of the spectrum.
Right. many of these infrared images, for example, from JWST, right? They have been RGB'd up in such a way that we see them. So when we see the purple or the violet colors there, that's not the violet. That's a color that was generated and then processed in our brains to make these pretty pictures. It's pretty cool.
Wow. Super cool.
All right, let's kind of fold back into some things we've just discussed with another question, this time from Sarah, who is currently in Kansas. Was she a train driver? What is so special about
in this moment?
Kansas is a great place. No, Kansas, home of the Runza.
All right, what is so special about photons that they go exactly the maximum speed, and any faster, they'd be moving backward in time? Is that speed, the speed of light, a barrier to them that if it weren't, they'd be going even faster? Do photons set the maximum speed objects can travel in our universe?
This is a great question. And I'll first start by making a clarification that if photons exceed the speed of light, they would not be moving backwards in time. Photons cannot exceed the speed of light because that's the definition of the speed of light is how fast a photon goes.
I thought you said futons there for a second.
Photons. Oh, photons can, yeah.
Yes. Flying sofa.
I swear I heard flying sofa.
That's a futon. It's kind of flying sofa bed.
But yes, the speed of light is a barrier of sorts, although it's a barrier that has come about for reasons we don't understand. The speed of light is the speed that light travels through vacuum. But that is a limit. The moment you have mass, you can't reach that speed. If you have mass and you reach that speed, you have become energy. You have lost your mass. You have become a photon.
Right.
So that's kind of the dynamic of how mass and energy intersect when you're approaching speeds up to the speed of light.
Yeah, but Charles, but let me open up that question a little more broadly.
Sure.
You're being a little tautological. Is that the right term? When you say the speed of light is the speed photons go. And if they went faster, then that would be the speed of light.
Yeah.
And I'm saying there is this number that we all measure. Why can't you just nudge the photon to go a little faster?
We don't know. We don't know yet.
Good. I like that.
We don't know yet.
And what then of the entire physics math description of particles that exist faster than light that we call tachyons? Because they go backwards in time.
Yeah.
So why can't a photon just step across the boundary, become a tachyon, and then go backwards in time? Why are you preventing that?
The existence of tachyons has never been shown. Theoretically, they are possible. There was one professor visiting once I was listening to, and I asked a question about tachyons, and he cut me off right after the word tachyons. He said there was a fevered imagination dream state invention of people in the 60s who were high on something. They don't exist.
That's about when it came in.
Okay.
Yeah.
So I do not comment on this tachyon concept because I have not seen any papers or read anything that suggests that they actually exist. And that is the mystery. That's the what we don't know part, right? We know how to slow down light. We can bring light down. And in fact, we have even stopped light. Lena Howe at Harvard has stopped light.
Frozen light.
Frozen it for a brief moment in the lab, right? It's really quite amazing.
But just the idea that, and when you think about it, I mean, why not? Because every time light goes through a medium, a transparent medium, it goes slower and slower and slower.
Couldn't there be a medium where it speeds it up?
The most empty medium we have in the universe is vacuum. And so that is the maximum speed, right? You can think about the other way. Say we have light going through air and we want to speed it up. We pump the air out. And now that speed has been increased. But that's as far as we can get, right? Absolute vacuum is as empty as we can get, just as absolute zero is the coldest that we can get.
But suppose you don't even have space. Maybe it goes infinitely fast.
Through what?
Space is creating a limit for light.
Yeah, but what is the light traveling through?
Through
if there's no space. If there's no space.
Not space.
If not light is traveling through not space, then it does not speed, right? And so it could be anything you want. That's a great question, though. No, these are fun questions to think about.
Yeah.
Okay,
I mean, there's really neat to think about.
You're casting shade on tachyons. I want to just resurrect them briefly before we get to our last question.
Sure.
The point there is all of Einstein's equations show you cannot just like you said, Charles, you cannot accelerate matter to the speed of light at all, because everything blows up. The equations all blow up.
Mm-hmm.
However, if you grant something's existence at faster than the speed of light, not crossing the boundary, then you can derive a whole set of properties on the other side of that equation.
Yes.
Where time goes backwards.
Right.
And so that's, they didn't just pull it out of their ass.
Ooh.
No,
That's really cool, though, because that means there could be an entire universe that is running backwards that we can't even see.
And the slowest they can move is the speed of light.
Is the speed of light.
It will take an infinite amount of energy to slow it down to the speed of light.
Right.
Yeah, it's like opposite land,
Right.
you know?
That's the nature of what tachyons are, which are really great. And mathematically, it is consistent to an extent. Many things are mathematically consistent to an extent which do not reflect reality, right? And many of them, which were invented a long time ago, turned out to reflect reality, at least partially, in such a way. But in this instance, nothing has yet suggested that the tachyon structure or the existence of such things has any kind of intersection with our universe, where everything travels at the speed of light or slower.
Mm-hmm.
Great point, though.
Let's get one more in. Can we get
One more,
question?
yeah. So this is from Leon Rivera. Leon hails from Jupiter, in Florida. Don't get too excited.
Which is its own planet in a way, too.
So disappointing. So disappointing.
It's all in the timing.
No.
He's a big fan of the show. I'll cut his whole question down. He says, I would love to know what both doctors think is the greatest achievement in astrophysics of all time. And then he puts in brackets so far.
Dang.
Well, you go first.
Okay.
Charles.
If we're talking about in my lifetime, the greatest achievement that has enabled other achievements on a way that nothing else has been able to, it is the successful design, construction, launch, and operation of the Hubble Space Telescope.
Okay.
It is the thing that has enabled more discovery in astrophysics than anything else in my lifetime. If we need to talk about just the ultimate discovery, the thing that sort of is the most fundamental thing in astrophysics, period, I think it is the confirmation of the existence of the Big Bang, a thing where the universe was once small and is now large, that there was a moment where you could extrapolate to a time equals zero from which everything we see and know has evolved to this point. How, the specifics of the Big Bang, we still don't know. There's still a lot of things that are like in there. It could be a cyclical Big Bang, could be an inflationary Big Bang, but there was a Big Bang.
And the reason there was is because we can see it, right?
Yep. The cosmic microwave background detection, the expansion rate of the universe accelerating, the nucleosynthetic relationships of how much hydrogen, helium, and other elements there are in the universe, all of that conclusively, with beyond a reasonable doubt.
And the reason why I said that is because there's a lot of people who say that that is the religious leap of faith that you guys as astrophysicists make, which is juxtaposed against the leap of faith that people make when they say, well, there was a creation or a creator.
Right.
The difference is the Big Bang is supported by data.
That's right. We did not take a leap of faith.
Difference.
Right. We did not take a leap of faith that was not evidence-based. That's the fundamental line.
Well, that's what I'm saying. You can see it. You can see it. You can actually see it.
In the middle of the 20th century, a pope actually said, you know what? The Big Bang has been shown scientifically to be true. Therefore, God exists. Now, that is a leap of faith. Right?
Mm-hmm.
Right.
Mm-hmm.
Right.
The leap of faith that religious leader made is not the same kind of conclusions to which Neil and I and our colleagues have come to, is because we are evidence-based.
And that's why y'all going to hell. That's why you're going to hell.
If hell exists, Lord
How dare you, Sal? I don't know that I could add to that. Those are really good important discoveries.
Well, they're just off the top of my head, Neil. You know that we can think of 100 different awesome things. I mean, this is just what's off my head.
The Hubble telescope is objectively the most productive scientific instrument ever built.
Yes.
You measure how many research papers, how many different collaborators, how many different nations participated in research results that derived from that telescope. So, so that's not just your opinion there. You've got there's metrics to back it up. I would mention two things. Number one, for the 20th century, I would say the discovery that the heavy elements in the universe owe their origin to heavy stars, massive stars that have manufactured them in the crucibles of their nuclei.
Yeah, Burbage, Fowler, and Hoyle. Yeah,
and
marvelous work.
Scatter that enrichment across the galaxy, allowing complex molecules. And in the limit of complex molecules, you get what we call life. That discovery was at 1957, just right mid-century, by the Burbage couple, Jeff Burbage and Margaret Burgess.
And Fowler and Hoyle.
Fowler and Hoyle. Fowler would ultimately get a Nobel Prize. That discovery borders on the spiritual, enabling us to recognize that we are not simply alive in this universe. The universe is alive within us. We contain the ingredients of the stars. That is a kinship that some people use it to feel small, but I use it to feel large. When I look up at the night sky, I feel a sense of participation in the great unfolding.
Y'all not so special. Y'all not so special. All that stuff is inside me too. Okay.
We are as amazing and as ordinary as every star in the sky.
Wow. I love that. Oh, that's so cool. That's great.
Except there are more stars than there are people.
Yeah.
So
right now.
Right now.
We've only gotten started, right?
And lastly, if I go through all of time, I would say it is not just the supposition, but the evidence that the universe is knowable.
Oh, super philosophical. Awesome.
No, because if everything in the rest of the universe were completely different from what happened in your laboratory, the universe would not be knowable. If different laws of physics applied on every planet and every galaxy and we just have our own little world here. But the fact that we measure things, objective things on Earth, and find them playing out elsewhere in the universe is an extraordinary fact.
Yeah.
And it wasn't that long, 300 years ago, where we found that the orbit of Uranus did not follow Newton's laws. And people suspected, well, because Uranus was a newly discovered planet in the era of Newton's laws of gravity. And people said, I wonder if we found the edge of the applicability of Newton's law of gravitation. You go out there to Uranus, it doesn't apply anymore. And someone said, well, maybe it does. And there's another planet out there whose gravity we have not reckoned. And they searched and they found Neptune. They found Neptune. Oh my gosh. And after that, we would find binary stars orbiting following Newton's laws of gravity. Binary galaxies, all of this. And so the fact that the universe is knowable, oh my gosh, that's got to be the most profound fact of science, of any scientific discovery there is.
You sound like you should marry the universe.
What are you, middle school? So I hope that those two points of view, and I agree, Charles, we could have gone on for another hour.
Oh, yeah.
Listing these achievements. So Gary, thanks for putting this together.
You're welcome. Thank our Patreon members. Their curiosity is fascinating.
And Charles, good luck on the release of your book.
Thank you so much.
Give me the name and title again.
It's called The Handy Quantum Physics Answer Book.
Excellent. And it's at better bookstores near you. All right. Chuck, always good to have you, man.
Always a pleasure.
Neil deGrasse Tyson here. Keep looking up.